let's work some with the random effects model. So I went ahead and showed you the fact that I made up this data set so you could see how that's done. But the basic idea is I've got 3 different types of coding, coding 1, say coding 2, and coding 3, and then 2 different methods. I labeled them method 0 and method 1 in SAS, but you can call them 1 and 2, whatever. And the basic idea is I've got this factory where I'm producing widgets, and I randomly select a method and a coding, and then I randomly select a widget to apply it to. I apply it, and then I test, say, the conductivity of the widget. That's going to be my Y variable there. And everything's done on the same day, etc., etc. So we don't have any confounding here. Well, the problem with this is we can't use this particular piece of code right here. It actually doesn't do what you think it's going to do when you declare something to be random. So instead, we have to actually kind of program this ourselves, in the sense that what we're doing is we're creating the denominator for this F statistic. Let me show you a little more specifically what's going on with the theory. So the idea is our expected mean squares are these values here. This is a handout by Dr. Longnecker. You can see how to get there at this website. And in this scenario, Q is, say, these sums defined down here. The idea is the null hypothesis is really mu1 dot bar equals mu2 dot bar equals mu3 dot bar, where these are the average conductivity levels for each of the 3 coding types. So I've written mu1 dot bar is mu2 dot bar is mu3 dot bar. That's the null hypothesis. If those 3 things are equal, then this sum will turn out to be 0. So if this sum is 0, then sigma squared E divided by sigma squared E will be 1. And that's what you're looking for, is something to give you an F statistic of 1 when you actually make that division. And that's what happens in SAS by default. So this is F1 and F2 are fixed. In that case, SAS is great. It gives you the right thing. So if I go ahead and run this, you can see if I take this method, mean square, 0.0103, and then divide it by the mean square error, 0.00277, then I should get an F statistic of 37.40. And that's all well and dandy. The problem is when I have a random effects model, the expected mean squares are not these, but if you scroll down, if both factor 1 and factor 2 are random, so suppose we have randomly selected 3 methods out of all possible, two methods out of all possible methods and 3 coding levels of all possible coding levels, then these are going to be my expected mean squares here, and then in order to create our F statistics, we're going to have to divide by the interaction mean squares instead of the error mean squares. And so that's what I've done in this SAS code, is I've set up the errors to be method by coding interaction for both factors. So this is the factor that I'm interested in testing, method, and then the error mean square that I want to use is the error mean square from the interaction rather than the true mean square error. And then, so if you want to double check that, you can go in here and take the mean square for method, which that's the same thing as this one up here. By the way, this code, this output is the default output, and this is the output that I got from the test commands. So when I said test, something, 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 these are my 2 tests that I'm running. So if you take this mean square 0.0103 and divide by the interaction mean square that we got from our ANOVA table, then the resulting F value is indeed 59.8. And then same thing if you do the same thing for coding and use that interaction mean square. One more thing to be careful about when you're doing this is that if one factor is random and the other factor is fixed, you're going to get two different tables depending on whether you use this sum to 0 constraint or setting that last factor equal to 0. Most computer programs, including SAS, use this last factor, level of the factor equal to 0 constraint. So while you see this in a lot of textbooks, it's not right for SAS and as well as most computer programs. So if you're used to seeing these as your expected mean squares, just note that SAS is not doing that. And so you don't need to worry about, well, which factor is random and which factor is fixed if you have a two-factor experiment, so that you can divide by two different things in your F statistics. Rather, because SAS uses that former constraint, you're going to divide both by that interaction mean square. So the code that I have written is correct whether you have one factor that's fixed and one factor that's random, or whether both are random.